Hello, this is Randy, WB0SMX. Going to be going through the 8640 Junior Hartley Oscillator circuit this morning. I've already built this in Spice, and I just wanted to cover a couple points that some people may be having trouble with, because it's kind of hard to get oscillators to work in Spice unless you know a couple tricks. So what I'm going to do is open up that circuit that I saved earlier. This is my 8640 Junior Q1 Hartley oscillator, and here you can see that we've got our tapped inductor, and on Wes's schematic he shows that as a single inductor, but in order to model it in LTSpice I created two separate inductors and connected them together basically. And there's some other things we're going to do a little later that will add some mutual inductance to those and make them a little more realistic. Some other things of note: the model that I had for diodes did not include the 1N4152 that we got in our parts from Doug Hendricks. And so I'll show you how to add a model for that part and other parts to the standard component models that are included with the LTSpice. So when we initially try to get this oscillator going, you might be tempted to just use that same command down here that we used with the Q4 buffer that I demonstrated earlier, in which we say basically start it up and capture from 0 to 1 microseconds. And so if we do that, what we'll find is that when we go to probe the oscillator circuit, that it's not oscillating. It's just 0 volts, and the reason for that is that in Spice, or in the real world I should say, when you start up a circuit, there's noise, natural noise in the in the world basically, that will be induced on various components and stuff, and thermal noise, things like that, and the voltage starting up and going from 0 volts up to the supply voltage will kind of kickstart the oscillators and stuff. But in Spice we don't have that unless we tell it to do it. So what we have to do is, if we come down here and right click on this operation, for now we'll leave this at 1 microsecond, although that's going to be a problem a little later. But to get an oscillator to start, what we need to do is tell it to start the external DC supply voltages at 0 volts. So they'll start at 0 and they'll ramp up very quickly to the 6 volts in this case. And that'll give us a kind of a kickstart for the oscillator. So I can say OK there, and I'll go ahead and save that. And you can see that it added the parameter startup to the end of our operation here. So if I run the simulation now, it is going to oscillate, but we're not going to see it because we're only looking at the first microsecond. So if I probe on this, you can say, yeah, well, it's kind of trying, but basically what we're seeing there is that we didn't really wait long enough for the oscillator to start. So nice, got a little jet airplane in the background here. Kind of wait for that to pass. So what I'll do is, instead of only looking at it for 1 microsecond, I'm going to look at it for 100 microseconds. And it'll take a little longer to run, but we can then save that and run it again. And there, it's finished, and we can then probe and we see, okay, our oscillator is actually starting to run. About 30 microseconds in, it finally gets stable enough to begin oscillating and stay stable. So that's what you have to do for the startup thing. Now, one of the things we find with the Hartley oscillator is that we have no mutual inductance specified for these coils. So even though in the real world, if I was to wind this bottom half of this coil backwards, in the real world that would cause it to not oscillate. In this SPICE model, as we have it now with no mutual inductance, it doesn't care. So what I can do is grab that and select it and do a Control R a couple times to flip it around, connect it back in, and let me resize it there. There we go. Escape. So now if I rerun this guy and let it finish and then probe our circuit, it still oscillates. That's not very realistic. So to make it a little more realistic, what I like to do is specify a mutual inductance between these two coils. And the way to do that is with the SPICE directive. We want to do a K, and I don't know what the K stands for, but it causes a mutual inductance transformer, I guess, between the two coils, L1-A and L1-B. And I'm going to specify the mutual inductance of being 0.9. So I'll say OK there, and I'm going to put that somewhere close to the inductor, although it doesn't have to be. It can be anywhere on the window. So go ahead and save that. So now if I run it, you'll see that our dot is on the bottom for this coil and on the top for this coil, which means that they are not in phase. So if I run the simulation now and look at our output, well, it tried to start, but it couldn't really get started. And that's because those coils are now out of phase, and SPICE knows that they are out of phase. So I can grab that bottom inductor again, do a couple Control R's to flip it back around, and click on it to set it in place. So now we can see, if I escape here, we can see that the little dot is on the bottom of the first coil, little dot is on the bottom of the second coil, and they are now in phase. So if I save that, rerun it, and probe our circuit, it's back to where it oscillates. So that's a good thing. Okay, some other things we can do. If we want to zoom in on the waveform and see more detail, we can do that. If I do it up here where it's kind of stable, I just want to get a few cycles there, so we can do that. And there you can see that we've got a pretty clean waveform there. It's very nice. I'm going to rerun, look at it again. So then if we want to look at the startup, we can say grab this part here. We can say that it starts very small and it gets larger as it goes on. So that's kind of cool. Not really thinking about how to restart this thing without running through the whole thing. As you can tell, this is kind of unrehearsed. Okay, so another neat thing, if I grab it in a stable portion here and then I right click on the waveform, I can come down here to view, and we can actually run an FFT analysis on this, a spectrum analysis basically, on the waveform that we selected. And it will automatically come up with the waveform that I clicked on, and we can just say OK, and pretty neat. It shows the fundamental frequency here and some spurs down here, but we can see that our fundamental here is running at about 11.669 megahertz. If you look in the bottom left corner of the window, it shows the frequency that you're at according to wherever you push the cursor. So over here on the right hand side it's 17 megahertz, left hand side it's 8, but where our fundamental is right now about 11.6 megahertz. So what we can do is we can increase the value of these capacitors to their maximum value and see how that affects the oscillation startup and the waveform and the FT analysis. So if I right click on that and put in 35 picofarads, and on this one we'll set it to 365 picofarads. Then we'll run our simulation again and look at it here. Nice clean waveform, 6 volts peak to peak, very nice. So I'm going to select a sample of the waveform here and right click on it, go to view, FFT, select the correct node. So now we're looking at about 9.95 megahertz at the low end with the high value capacitors for our fundamental frequency. So we can go the opposite extreme. We can say, well, let's go to a realistic value. It's probably not going to get below 1 picofarad on any variable capacitor, probably more like 3 picofarads or so. But we'll go to 1 picofarad and say OK, and then we'll run our simulation again. Look at our waveform. Uh-oh, did not work. Well, let's try something here. Let's look at changing this diode to the one specified by Wes, which I've already put in the library. Say OK and run it again. This time it's working on it. So now it oscillates, nice clean waveform, and it's a little tighter than I'd like it. Let's go there. So if I right click, go to view, FFT, OK. So we're looking at about 36 megahertz there for fundamental frequency. And since we changed the component, let's go back and set these to the maximum values, 365 picofarads and 35 picofarads. Run the simulation again. And use the left click instead of the right. So now we're looking, if I right click on this, view, FFT, OK. So on the low end we're still looking at 10.1 megahertz. So the diode made a difference in this case. It could have different junction capacitance or something like that that could have been affecting it. So it's nice being able to have the correct models in there. And you saw that I was able to select that by doing the right click and then pick new diode and then basically going through the list. I had added this guy at the end of the list prior to starting this demonstration. So while we're on that subject, let me show you how to add a component to the library. Oops, I'm going to keep that there. Okay, so what you have to know is where the components are stored. And so I'm going to bring up a Windows Explorer window here. And if we start at C:, we can go to Program Files, and the directory that this is in is LTC, Linear Technologies Corporation, and then the LTSpice 4 directory. There's a library folder, and then within the library there's a components folder. So we go to components. This is where our standard models are, and if we open the standard.diode model, we can see that it lists the models for all of the different diodes that we have modeled in there. So what I did is I did a search on the internet for the 1N4152, and about my second or third hit I came across this guy here, National Library, and if I scroll down there you can see they have models for a bunch of different stuff. I'll go ahead and add the 1N4153. So all you do is highlight that first line there and copy it to your clipboard. I use Control-C. And then at the end you can click on that, hit enter, and do a Control-V, and that adds the line that we just copied. And I go ahead and just to make it the same as all the rest, I make it lowercase. Okay, had a little cut and paste error there, but I ended up going back and entering the 1N4153, and he's got all of his values here, and then at the end I'll put the I'll go ahead and copy and paste the manufacturer and the type. Control-C, Control-V. Okay, so then I can save that. And close it. So now when we go to pick a new diode, if we go down to the very end, we see that we can pick the 1N4153. So it's pretty easy to select or add new components to the library. I don't even know what a 4153 does, but I'm going to run it anyway and see if it affects us any. Probably not. Yeah, it looks about the same. So that's basically the gist of it. Change this back to the correct diode and save it. So what did we learn? Well, we learned that we can use a tapped inductor by creating two inductors in SPICE and connecting them together, and putting a SPICE directive up here that creates a mutual inductance between the two. which makes them so that they act more like a real inductor. We learned how to insert new components into the library, how to do the FFT analysis, spectrum analysis, and how to change component values on the fly and see what happens. So there you go. Have fun with your own. This is Randy, WB0SMX. Catch you next time.